Welcome everyone to this Winward Academy lesson to review the rare and random concepts that come up on SAT and ACT math. So together today we're going to go over modeling growth, we're going to go over statistical terms, do some fun review of synthetic and long division, and then also review matrices and vectors. So these 5 topics don't come up a whole lot on the ACT and SAT. They tend to be harder questions, and then when they do come up, again, they're kind of closer to the end when the harder questions come. And it's one of those things that if you're really trying to go for a nearly perfect score, you really need to know these concepts because, again, even though they don't come up a whole lot, when they do come up, you want to make sure that you're ready. So let's go ahead and get started with modeling growth questions. Now, the first topic we're going to go over with modeling growth is the difference between linear growth and decline, right? Growth, of course, meaning increasing values, decline meaning decreasing values. And what's the difference between when something grows or declines linearly versus exponentially? So let's review that first, right? Because if we look at answer choices A and B, they both have linear changes, growth and decline. C and D have exponential. So really quickly, let's review what it means with a linear change. So if you are growing linearly or declining linearly, it basically means that you are seeing the same amount of change each time. So when we look at the data given to us, right, where we have these different weeks, and then we have different populations. Now, if this population was growing linearly, and it's definitely growing, right, because look at these numbers, they're increasing each week. So we know for sure that it's not going to be decline. We know for sure that it's going to be growth. So the first thing I'm going to do is get rid of my 2 answer choices with decline. We definitely know that it's growing because we're going from 10 to 100, 100 to 1,000, 1,000 to 10,000, etc. The numbers are getting bigger. But how are they getting bigger is the question between whether the answer is A or C. Now, if it was growing in a linear fashion, then each time it would go up by the same amount. So let's pretend it was growing and each time it went up by 5, right? The number would go from 10 to 15 to 20 to 25, etc. Now, when we look at this, to go from 10 to 100 would be increasing by 90, but then to get to the next one, we would add 90 again, but that only puts us at 190, right? But the number that we want is 1,000. That means that we are not seeing a linear change. Because remember, with a linear change, it's the same amount each time. With an exponential change, there's something you're multiplying or dividing by each time. And if we look carefully, right, to get from 10 to 100, we multiply by 10. Then we multiply by 10 again to get from 100 to 1,000. Then multiply by 10 again, and then multiply by 10 again. So because we are multiplying in between each of those terms for the population, we know that it is exponential growth. Because again, the key difference is that linear means that it's increasing by the same amount. Exponential means there's some sort of factor that we're multiplying or dividing each time. All right, now we're going to go over 2 questions together that both have to do with compounding interest. So the first thing I want to do before we read the question is give you the equation for compounding interest. So our equation, or the one that's typically used, is that y equals a, where a is the initial amount of money that's invested, times 1 plus r, where r is that percentage that the interest is compounding, and that's being raised to a power, and I'm going to write number of times. And let me explain why I'm writing the number of times. That exponent value basically represents the number of times that the interest compounds. So if it's been 5 years and something compounds once per year, then that exponent would be 5. But if it's been 5 years and something compounds twice per year, well then for each of those 5 years, we would have seen a change with that interest applied twice, so we would see a total of 10 times that interest compounds. So again, this equation, and we're going to practice with it several times, so if it doesn't feel clear right away, that's okay. We're going to go through it together. All right, so let's learn about Julie and what she's done here. So she opened a bank account it earns 1.25% interest. So the first thing I'm going to do is I'm going to write down that R equals 1.25%. Now really quickly, you're never going to plug in percent values for R. You always need to get it into the decimal form. So let's do that quickly. Remember, whenever you see a percent, you rewrite as divided by 100. 1.25 divided by 100 is the same thing as moving that decimal 2 places to the left. So that turns into 0.0125. So we now have our value for R. That is 0.0125, and notice here is that R in our equation. Okay, back to the question. Julie opened a bank account. It earns 1.25% interest compounded annually. Okay, so it compounds 1 time per year. If something happens annually, it's once per year. Her initial deposit was $150. Okay, so this initial deposit of $150, we're going to plug in for A. And then here's the expression that she used to find the value of her account after T years. Now remember that if something happens every T years, and it happens once per year, then the total number of times that we're going to see this interest compound will be T, right? Because if it's been 3 years and it happens once per year, it will have happened 3 times. If it's been 5 years and it happens once per year, it would have happened 5 times. Okay, so now let's get to our question. And by the way, these questions are coming from a past SAT, right? That's why these are grid-in questions style, right? We don't have multiple choice to choose from. We actually have to solve something and then write in a number for our answer. So the question is asking us, in that expression that she uses, 150 times x to the power of t, what is the value of x in the expression? Well, let's use our equation that we have right over here and plug in our numbers, and then we can figure out what is x. So y, which is going to be the money in her account after t years, equals that initial investment of 150 times 1 plus our value of r. Remember that purple underline is 0.0125, all being raised to the power of t. So when we simplify, that's y equals 150 times 1.0125 to the power of t. Well, in her equation, the equation she used was 150 times x to the power of t. And we know that the equation is 150 times 1.0125 to the power of t. So the question, what is x? Well, guess what? X is 1.0125. So that is what we would write in to our grid-in answer. Okay, next question is about Julie's friend Tyler found an account that earns 2% interest compounded annually. Okay, so it's that same annual term, it's just happening once per year, but Tyler found something with more interest, 2% instead of 1.25%. Tyler made an initial deposit of $150. Okay, so the same initial amount of $150. The same time Julie made a deposit of $150 into her account. Okay, so the two friends both deposit $150 at the same time. Julie's is going to earn 1.25% compounding annually. Tyler's is going to earn 2% compounding annually. So now our question, after 10 years, how much more money will Tyler's initial deposit have earned than Julie's initial deposit? Okay, so here we go. We already know our equation for Julie's growth, right? For Julie, it was that initial deposit of 150 times 1.0125 to the power of t. But we know what t is, right? Because we know that it's going to be 10 years. So that's going to be our value of t, and I'm going to put a 10 there. So let's first figure out how much money is Julie going to have after this period of 10 years. Now remember, with your order of operations, we have to do 1.0125 to the power of 10 before multiplying by 150. So we're going to have 150 times, when you get your calculator, 1.0125 to the power of 10. It's going to be very long, 1.13227, etc. Do that multiplication by 150 and we find out that Julie's going to have $169.84. I'll put a little J for Julie after 10 years. So now let's figure out how much Tyler is going to have. Well, remember for Tyler that his rate is 2%. When you see a percent, you do over 100, so 2% is 0.02. All right, so what is Tyler's equation going to be? It's going to be y equals that same deposit, 150, times 1 plus his rate, which is 0.02, raised to the power of the total number of times that it changes. Remember, it happens annually, which is once per year, times 10 years, so t is 10. So the equation for Tyler is 150 times 1.02 to the power of 10. Just as we did for Julie, do that 1.02 to the power of 10 first. So we have 150 times, again, this is going to be really long, 21899, keeps going. When you do that multiplication, you get 182.85. Now, the question is not how much money does Julie have or how much money does Tyler have. I'll put a little T here for Tyler, by the way. So here's Julie, here's Tyler. The question is how much more money does Tyler have? So the answer to our question is simply to find the difference, 182.85, minus what Julie has, 169.84, right? Where we're basically doing Tyler minus Julie. So the correct answer to this question when we do that subtraction is 1301. So in your test booklet, right, you would write 13.01. Okay, let's keep going with modeling growth. This next question is our first example with a decay. Now I want you to use the same equation, except, so here's our initial, instead of doing 1 plus r, which is what we do for growth, we're going to do 1 minus r, which is what we do for decay. Still to the power of the number of times that you see that, that change occur. Okay, so let's figure out what we have here. The rate is 15%. So the first thing I'm going to do is just put that r equals 15%. Remember, we can't put a percent in there. We need a decimal. That means that r is 15 divided by 100. Remember, when you see a percent, divide by 100. So r is 0.15. So I'm going to take that value, 0.15, plug it in over here for R. Then they tell us that the initial amount of the substance is 250 grams. So I'm going to put that 250 right there for A. Which of the following functions, F, models the remaining amount of the substance in grams T years later? So it's been T years, which of course is important to know so that we can figure out that exponent. It's been T years, and it decays at an annual rate of 15%. That means that that rate changes once per year. It's annual. It's not semi-annual, which would be twice per year. It's not monthly, which would be 12 times per year. It's an annual thing. So the total number of times is just going to be T, because after T years and it happening once per year, the total number of times will be T. Okay, so let's plug in what we have. We have that y equals that value of A, which is 250, times 1 minus r, which was 0.15, all raised to the power of t. Last step to get our equation, 250, 1 minus 0.15 is 0.85 to the power of t. So when we look at our answer choices, which answer choice gives us this equation? And the answer is A. All right, we've got two more. William deposited X dollars in his investment account on January 1st, 2015. Okay, so really quickly, let's get our equation. It's y equals A, 1 plus r to the number of times, right? If somebody's depositing money into a bank account, we're going to assume right now that it's going to grow, but we'll go ahead and double check that it's a plus r, not a minus r. Okay, so he deposited X dollars into his bank account. So that initial amount that he deposited is going to be an X. So I'm going to put an X here. The amount of money in the account doubled each year. Okay, so this is where it gets a little bit tricky because how do we figure out what R is if something is doubling? So I'm going to go like this. I'm going to put R equals double. Now we have to think for a second because what is the rate if something doubles, right? You basically take 100% of that number, whatever it is, and then you add it back to itself, right? So if you started with 5 and you wanted to double it, you would take that same value of 5, add them together, and then get 10. So essentially when you double something, it's really like you're increasing by the exact same amount. So you're not increasing by half of it, you're not increasing by a third of it, you're not increasing by 2% of it, you're increasing by 100% of it. So that means that when you double something, your value of R is 100%. Because again, when you're doubling it, you're taking the same amount twice. And if you're taking that same amount, again, you're taking 100% of it. So if R is 100%, well, if we want to convert that to a decimal, remember you just take the percent, which is 100. When you see the percent, that means divided by 100. Well, guess what? R is just 1. So what are we going to do with that R equals 1? We're going to plug it in over here. Now, how many times does it change? Well, let's see. It looks like to me that it's been 5 years, right? Because we're going from 2015 to 2020, and it's the same day. So we know that it's been 5 years. And then does it say that it happens? It says that it doubles each year. That means that the rate applies once per year because it happens each year. We see this factor of R where it's doubling. So that means that that power for the number of times is the number of years that it's been, which is 5. Okay, there's a little bit more information that they've given us. It says the amount of money in the account doubled each year until William had $8,000 in his investment account. That means that the final amount of money he has is $8,000. The initial amount of money he has is X. 1 plus, remember when we're doubling something, that R is 100%. So it's the same thing as 1 being raised to the total number of times that we see a change, which is the 5 years. So now we can go ahead and solve for X, right? What is the value of X? That's the question. So we have 8,000 equals X times 2 to the power of 5. That means 8,000 equals X times 2 to the power of 5, which is 32. To get X by itself, I'm going to divide by 32 on both sides, and I get that X equals 250. Notice for this question, we do not have multiple choice. That's because it's coming from a past real SAT, where this question would be a grid-in question. All right, one more with modeling growth. This is our last one. In planning office space for city workers, an engineer estimates that, starting from the present, the number of city workers will increase by 10%. Okay, so let's just start right there. R is 10%. That means R is 10 over 100, which means R is 0.10. Okay, so we figured out what R is. It's going to increase by 10% every 5 years. Now that's key, okay? It's not happening once per year. It's not happening twice per year. It's actually only happening every 5 years, which means that after 5 years, it's happened once. After 10 years, it's happened twice. After 15 years, it's happened 3 times, right? So it's only happening every 5 years. That's going to be really, really important. If there are currently 5,000 workers, okay, so our initial amount is 5,000. Oops, let me first write our equation. Y equals the initial amount times 1 plus RR to the power of the number of times that we basically increase something by that factor of R. So what do we know? We know that A, that initial amount was 5,000 times 1 plus, we know that R, we just figured out, was 0.10. Remember, here was our R value. I'll go ahead and underline so it's all marked. Same thing with that initial value, that 5,000. Okay, so here we go. Which of the following expressions represents the estimate of the number of workers T years from now? So we have to think carefully here because we need to figure out, okay, well, what is the total number of times, right? What is this exponent going to be? If it's been T years, but it only happens every 5 years, then the total number of times that we would have actually seen this 10% increase would be the total number of years T divided by 5. That part of this question is the hardest part. You have to know that that exponent is T divided by 5. Because again, if T is the total number of years, let's pretend it's been 20 years, T is 20. Well, how many times would we have seen this 10% increase? Well, if it only happens every 5 years, in 20 years, we would have seen it 4 times, right? But how did I do that? I took the total number of years, 20, divided by 5, and then I know that it only changes 4 times. So again, the hardest part of this question, so I'm going to put a little kind of star over here next to it. The hardest part was knowing that that exponent power was T divided by 5. It would have only been 5 times T if something changed 5 times per year and then it had been T years. So our final answer, sorry, I know I'm getting very sidetracked explaining that exponent, but it's the hardest part, so I want to make sure you understand. So it's going to be 5,000 times 1.1 to the power of T divided by 5. So it looks like our correct answer is option D. Let me just double check. 5,000, 1.1, yep, to the power of T divided by 5. So that is the correct answer for our last modeling growth question. Now, we also see that statistical terms come up on the ACT and SAT again in those kind of rare and random, later, harder questions. So we're going to go through 6 examples together of statistical terms type questions. So for our first one, it says to test a new dietary supplement, each of 150 volunteers was assigned a distinct number from 1 to 150. So we have 150 people, each one gets a distinct, so each one gets a different number. Next, 75 balls were drawn from among 150 balls. Okay, so it's just they're leaving it up to chance, put a hand, draw a ball, okay, that number goes with a person. The balls were numbered the same way as the volunteers so that the 75 volunteers whose numbers were drawn would receive the new dietary supplement without bias, right? So the key thing here is that they're saying that because they did this random selection of just picking numbers randomly, there's no bias in the way these people were selected. The other volunteers received a placebo. Okay, so again, we've got 150 people total. 75 of them chosen at random are the ones who get the supplement. And then the other 75 whose names are not chosen get the placebo. And just to make sure that you all know, right, a placebo condition is basically you're not going to tell those people whether they're getting the real supplement or not. You're going to give them a pill that looks and smells and tastes just like the real supplement so that, again, they don't know that it's different. And then if you really want to know, does this supplement have an effect? Well, then the people can't know whether they're taking the real thing or a fake, kind of sugar pill equivalent version. Okay, what happens? So we've got the 150 people divided into these 2 groups. 1 month later, the 2 groups were compared. Which of the following best describes the company's testing? Well, the first thing is that I want you to eliminate options A and B because they say that it's non-randomized, which is incorrect. What was described here is absolutely random assignment, right? Each person gets each of the 150 people gets a number, and I'm going to pick 75 of you at random. So it's definitely random, and because I'm putting people into 2 groups, and then I'm going to compare those 2 groups to each other, one group gets the supplement, the other group gets the placebo. That is an experiment. So the correct answer to this question is that it is describing a randomized experiment. Let's look at our next question. A study was done on the weights of children at a primary school with kids in kindergarten through 3rd grade. Okay, so I have a primary school. I've got kindergartners, first graders, second graders, third graders. A random sample of students was weighed, and students were checked off to make sure they weren't counted twice. Okay, so that's just good practice when you're doing some sort of experiment, right? You want to make sure that you don't count the same kid 3 times on accident, right? If you're including 30 people, you want to check them off to make sure that they're each only counted once. The sample included 30 kindergartners. So what I want you to notice is that the primary school had kids in kindergarten, first grade, second grade, and third grade. This sample is only with kindergartners. Well, that means that whatever you figure out from these data, you can only then generalize back to the kindergartners at the school. So we can't take a sample only of kindergartners when the school has kindergarten, first, second, and third grade, and then think that only studying the kindergartners is going to tell us something about the entire school and all of those grades. So chances are that is what this question is going to be getting at. They tell us that we get 30 kindergartners, of whom 40% weighed more than 46.5 pounds. Okay, so that means that 60% of them either weigh exactly 46.5 pounds or they weigh less than that. Which of the following conclusions is best supported by the sample data? So what I want you to do for this question is just read each answer choice, and then we're going to pick the one that is correct. It says the majority of all the kids at the primary school weigh less than 46.5 pounds. Be careful, if we only study kindergartners, I cannot generalize those data to the entire primary school. So for that reason, A is out. What about B? The average weight of all the kids at the primary school. We have that same problem again. I'm trying to generalize to all the kids when I've only studied kindergartners. So B is out. Also, it didn't even talk about the average weight, right? It just said that 40% weigh more than 46.5. It never said that that is the average. C, the average weight of all kindergartners at the primary school is 46.5 pounds. Again, so the problem here is that it didn't talk about the average, right? It just said that 40% weighed more than 46.5 pounds. So if it's not referencing the average, then I can't make a conclusion about an average. Can we conclude that approximately 40% of all the kindergartners at the primary school weigh more than 46.5 pounds? Guess what? That is the correct answer. Okay, so if I sample 30 kindergartners and 40% weigh more than 46.5 pounds, then the conclusion that I'm allowed to make is that somewhere around 40% of all the kindergartners, because remember, I only studied 30 of the kindergartners, so I took that sample of 30 of them. So from that sample of 30, if 40% weigh more than 46.5 pounds, then I'm allowed to conclude that, okay, well then, if I generalize that to all the kindergartners, approximately 40% of them would have that same characteristic of weighing more than 46.5 pounds. The problem with answer choice E is that once again, it's generalizing to all the kids at the primary school. You can't only study kindergartners and then generalize that to the entire school. If you wanted to generalize to the entire school, then your sample would have needed to have a balance of kids in kindergarten, first grade, second grade, and third grade. Our sample didn't. It was all kindergartners, so we can only conclude about kindergartners. Okay, next question. A polling agency recently surveyed 1,000 adults who were selected at random from a large city. Okay, so we know that we have random selection of 1,000 adults, and asked each of the adults, are you happy with your local government? Of those surveyed, 34% responded that they were satisfied with the government in the city. Based on the results of the survey, which of the following statements must be true? Must be true. So this is probably where they're going to be a little bit sneaky, because if you think, okay, out of the whole city, I sampled 1,000 adults and 34% of them are happy. Well, then you have to be careful, because if I took another sample of a different 1,000 adults, maybe 38% are going to be happy, or maybe 30%, or maybe 50%, right? We can't know. We can maybe estimate that approximately the same amount would be reflected of that approximate 34%, kind of plus or minus an error. But no way can we say, we studied 1,000 people, so we know for sure that out of everybody, 34% like the city, right? We cannot make that conclusion. And that's likely what these answer choices are going to be a little bit sneaky about. And that's exactly what we see in option 1. It says, of all the adults in the city, 34% are satisfied. Remember, we can only make approximations from our sample of 1,000 adults. Unless you survey, let's pretend 50,000 people live there. Unless you survey all 50,000 of them, you can't make a statement about what all of them would say. If you only sample a subset of that full population of the whole city, if you just take a smaller sample, then again, you're doing that to make your best guess or to estimate or approximate what could be true for the entire population. But that's the point of sampling, right? You're trying to understand something about all 50,000 adults, so you take a sample of 1,000 of them, and then you're trying to approximate or make your best estimate about what the full population would say. But that doesn't mean that each time you take a sample of 1,000 that you're going to get the exact same result over and over. Okay, so which one must be true? Option number 1, Roman numeral 1, is definitely, it doesn't have to be true. It could be true, but it doesn't have to be true. So that's why it's out. What about option 2? If another 1,000 adults selected at random were surveyed, 34% of them would report they are satisfied with the local government. Okay, again, option 2 could happen. We could sample another 1,000 who could have the same 34% who approve of the government. Or of that other sample of 1,000, we could have 35% who approve, or 30%, or 20%, or 40%. It doesn't have to be exactly the same when you take another sample. So if we're looking for what must be true, option 2 doesn't have to be true. It could be true, but, it doesn't have to be true. What about 3? If 1,000 adults selected at random from a different city were surveyed, okay, well, be careful, because now we're even talking about a different city, and we definitely can't take a sample from one city and then generalize it to another city, right? And we can't guarantee, once again, that that new sample is going to have the exact same value of 34%. So, because this question was saying what must be true, the answer is none. None of those options must be true. Again, the difference here being that could they be true or must they be true? So that's where it gets a little bit tricky. Okay, we've got 3 more. A researcher conducted a survey to determine whether people in a certain town prefer indoor or outdoor exercise. The researcher asked 54 people who visited a local park for a run on a Saturday. 4 people refused to respond. Okay, that's normal, right? If you're doing a survey on the street, some people might agree to participate, others might not. Which of the following factors makes it least likely that a reliable conclusion can be drawn about the exercise preferences of all people in the town? So if I want to understand something, my population, right, is all the people in the town, and I want to understand, do they prefer to exercise indoors or outdoors? Well, there is a gigantic problem if I go to a park to then ask people who are there exercising outside, going for a run, whether they prefer to exercise inside or outside, right? Most of those people, if not all of those people, are just automatically going to say that they prefer outdoor exercise because that's what they're doing. They're exercising outdoors. So we did not do a good job of random selection. We have a huge amount of bias in this sampling method of going to a park to ask people if they enjoy exercising outside. So what factor makes it the least likely? Well, it's the one how we did not have random selection. And so the problem is where the survey was given. The fact that the survey was given at an outdoor facility, right, at a park where people are running, is a giant problem for these data to actually be reliable. If we wanted to do this study, we would need totally random selection, like not asking people at a gym or a park, but asking people in a space that has nothing to do with exercise, and then asking them if they prefer indoor or outdoor exercise. Next question, to test if exercise X is successful in improving grip strength, a research study was conducted. From a large population of college students with poor grip strength. Okay, so notice that what they did is they have all these college students and they just looked at the ones who do not have strong grips. Out of all of those college students who don't have strong grips, so let's pretend there are 100,000 college students who don't have a strong grip strength. 500 of them are selected at random. So again, we've got our full population and then we're selecting a sample of 500 of them. Half of the participants were randomly assigned to do exercise X and the other half did not. Okay, so we've got our sample of 500, half of them 250 do this grip exercise and the other 250, oops, that's definitely not 250, and the other 250 do no exercise. The resulting data showed that participants who did exercise X had significantly improved grip strength compared to those who did not. Okay, so we had this full population of college students with poor grip strength, took 500 of them at random, then randomly put them into two groups. Half of the students did the exercise, half didn't, and they found that the half who did, right, the students who did do the exercises showed stronger grips compared to the students who did not. So based on the design and results, which of the following is an appropriate conclusion? So which of these are you allowed to conclude? What about option A? Exercise X improves grip strength better than all available exercises. Here's our problem. We didn't compare exercise X to all other exercises. We only compared it to doing nothing, to doing no exercise. That means that you can't conclude anything about how exercise X compares to all others because you didn't actually do that comparison. What about B? Exercise X is likely, okay, I like the word likely because remember with statistics you're finding things that are approximate. You're saying that things are likely. You're not saying that it's 100% true for everyone. So exercise X is likely to improve the grip strength of people who have poor grip strength. Perfect. So we're only generalizing to the people from whom we sampled, right? Everybody, right? We had our population of people with poor grip strength. From that population, we got our sample of 500. So anything that we discover is only generalizable to people who do not have strong grips. We can't take this study where we only studied people with poor grip strength and then generalize to all people, even to people who have strong grips. So option B is definitely going to be the right answer because we're saying that it's likely that exercise X will improve grip strength only for people who have poor grip strength, right? We're not extending beyond. It's kind of that same example where we had a primary school with lots of different grades. But if you only study kindergartners, you can only generalize your results to kindergartners. It's the same thing here. We have lots of people with lots of different grip strengths, but if we only study people with poor grip strength, then we can only generalize our results to people with poor grip strength. Let's look at option C and go through why it's incorrect. Exercise X will improve the grip strength of anyone who performs this exercise. That gets at what I was just talking about. You can't generalize to anybody. You can only generalize to people with poor grip strength. What about D? Exercise X will cause a substantial improvement in grip strength. Again, we can only generalize our results to people with poor grip strength, not to anybody, who potentially does the exercise. Okay, last one that has to do with statistical terms. So first of all, it's really important for you to know that you don't ever have to calculate standard deviation, right? You're not going to ever need the equation for standard deviation where you're finding, the difference between each point and the mean, squaring them, adding them up, etc. You don't have to do that. Okay, what you do have to do is just understand the theory of standard deviation. And what does it mean if your numbers are more spread out and farther away from a mean versus if your numbers are closer together and therefore closer to the mean? Remember, the mean is going to be the average. So what I want you to realize is that with city A, so I'm going to do a little plot over here of city A. So for city A, we've got 1 inch, 2 inch, 3 inches, 4 inches, 5 inches, and then the frequency for the number of days where we can get that much rain. It looks like 12 is the highest value, so I'm going to make this go 5, 10, and then 15. So 5 days, 10 days, 15 days. So we've got a 1 here, then we have 12 days that it rained 2 inches, then 3 days here, and then 1, and then 1. Now let me plot city B. And what I hope you noticed about city A is that nearly all of your answers are at 2. That means that the average, right, so if I took my 1, 1, and then I took my 12 2s, my 3 3s, my 1 4, my 1 5, I added them all together and then divided by the 18 days, the average value for city A is going to be something a little bigger than 2. Little bigger than 2, right? So you had a lot of answers. 12 out of the 18 were all 2. And then the others were spread out and had very low values at the others. That means that most of your data points are 2s, and they're going to be close to the average, which is likely a number that's a little bit bigger than 2. Now let's see what happens in city B. So I'm going to use the same 1, 2, 3, 4, 5. I'm going to use my same 5, 10, 15. So what do we have? So 1 inch happens 6 times, so I'll do a little bit above 5. Then we've got a 2, and then a 2, and then a 3, and then a 5. I didn't do the best job with that, but anyway, hopefully what you can see here is that for city B, the numbers are way more spread out, right? We don't have 12 out of 18 values that are all the same of a 2. They're much more spread out. We've got 6 at one end with the 1, we've got 5 at the other, and then it kind of does more of a U shape than it does having that strong peak. That means that for city B, right, our average is probably going to be much closer to 3, and then we're going to have a lot of values like 1s that are going to be 2 spaces away from 3, and we're going to have more values like 5s that are also going to be 2 spaces away from that average around 3. So here our average is likely close to 3. So what does this mean about standard deviation? Remember, standard deviation is an indication of how variable your data are. How much, right, how much are your data points different from the average? Well, if we look at city A, where most of our data points are 2, and our average is going to be pretty close to 2, we're going to have a very small standard deviation. I'm going to write small standard deviation. But then if we look at city B, where our average is around 3, and then we have our numbers way more spaced out, and we have more values that are farther away from 3, the 1 and the 5, than we do close to 3, which would be the 2 and the 4, we're going to have a larger standard deviation. So again, city A is going to have a smaller standard deviation. City B is going to have a larger, so our correct answer is B. Standard deviation of rain in city B is larger, and that is because the values are farther away from the average. So when you have a data set where you have a lot of values, like you have a high frequency at just one value, right? We had 12 answers just for 2 inches. We're going to have a smaller standard deviation because our numbers are closer together versus if you have your numbers are more spaced out. So the correct answer for this last statistical terms question is option B. Next, we're going to review synthetic division and long division, probably 2 of students' least favorite things to do, so I'm just planning to go through it one step at a time with you. We're going to do a couple examples of long division and then a couple examples of synthetic division. So if they ask you the expression 4x minus 2 divided by x plus 5. Okay, so I have 4x minus 2 divided by x plus 5 is equivalent to which of the following? So they're basically just saying do this division. So let's do a little review of how we do this. So what you're going to do is you're going to start with your x, and you're going to think x goes into 4x how many times? And it goes into it 4 times. Now I'm going to do 4 times x is 4x, and then I'm going to do 4 times positive 5 is positive 20. Now that my numbers are stacked, what do I do with them? So you have to remember that with long division, now we are going to subtract these numbers. The whole point is that we can cancel the first term. 4x minus 4x is 0. It goes away. Negative 2 minus 20 is negative 22. So now you ask yourself, does x go into negative 22? And no, it does not, right? It would need to have an x term like negative 22x or x squared or x cubed. Then x could go into it. Because x cannot go into it, that is our remainder. So what we're going to do, so first let's do a little review of some of the vocabulary. So this one on top, this is called the quotient. And then right here, this one is our divisor. So when you do long division, your correct answer is basically your quotient plus the remainder. Oops, sorry, I forgot to label the remainder. Let me do that right now. Remember, this one here is your remainder. Okay, so it's the quotient plus the remainder over the divisor. So the correct answer here is going to be our quotient, which was 4, plus our remainder, negative 22, over our divisor, x plus 5. Last step is just to bring that negative out, because 4 plus negative 22 is just the same thing as 4 minus 22 over x plus 5. So that is going to be the correct answer to our question, which is option D, 4 minus 22 over x plus 5. So let's do another one. Same steps. I'm going to have 2a squared plus 3a, and then don't forget to put plus 0. Remember, you have to sometimes put in those placeholders if a term is missing. And because that constant at the end was missing, I have to fill its place by putting plus 0. And we're going to do that divided by a plus 4. All right, same steps as before. A goes into 2a squared, 2a times, right? That's because a times 2a is 2a squared. I do 2a times a, 2a squared. Remember, the whole point there is that I stack them, so when I subtract them, they go away. Then I'll do 2a times positive 4, which is plus 8a. Our next step, of course, is to subtract. We subtract because we want to cancel that first term. 3a minus 8a is negative 5a, and then I carry down the plus 0. So now we're going to do those same steps again. A goes into negative 5a, negative 5 times. Negative 5 times a is negative 5a. Negative 5 times positive 4 is minus 20. Let's do our subtraction again. Negative 5a minus negative 5a turns into negative 5a plus 5a. They cancel. 0 minus negative 20 turns into positive 20. And then because a cannot go into 20, we are done, and 20 is our remainder. So again, here's our remainder of 20. Up here, 2a minus 5, that is our quotient. And then over here, the a plus 4, oops, I can't spell divisor, sorry, that's our divisor. So remember, the final answer when you do long division is your quotient plus your remainder over your divisor. That means our answer is 2a minus 5 plus our remainder of 20 over a plus 4. So it looks like option A is the correct answer. Okay, so next we're going to look at a question that you could solve with long division, but I'm going to show you how to solve it with synthetic division. So it says one solution of the equation 2x cubed minus 5x squared minus 11x minus 4 equals 0 is x minus 1. Really quickly, I want to make sure you know what that means. That means that if you use long division, you would set it up as 2x cubed minus 5x squared minus 11x minus 4. That is being divided by, and again, if a solution is negative 1, then the factor is x plus 1. Because remember, the solution means that whatever you plug in for x, you get 0. So if I plug in negative 1 for x, well then I have to do plus 1 to get 0. So remember that if the solution is negative 1, then out here you have to write x plus 1. So your first option here, of course, is to do this long division to figure out what you have up here on top. That's then your answer, and then from there you can continue to simplify to find the other two solutions. Because when we take something that's cubed and we divide by x to the first power, we're going to be left with x squared, right? So we're going to then have two more answers. But what I want us to do for this question, because I think it's a great time to review synthetic division. So again, you can use long division to solve this question, but what I'm going to do is show you how to do synthetic division. So with synthetic division, you take that solution of negative 1 and put it in the upper corner. So notice we didn't change it to x plus 1. We're just keeping the number itself of negative 1. I'm going to take all my coefficients, 2, negative 5, negative 11, negative 4. So I'm going to put 2, negative 5, negative 11, negative 4. Now, when we go through synthetic division, the steps are a little bit different. First, we're going to add instead of subtract, and we're going to start by carrying down that first value of 2. Then what do? I go 2 times negative 1 is negative 2. Negative 5 plus negative 2 is negative 7. Then I do negative 7 times negative 1 is positive 7. Add down, negative 11 plus 7 is negative 4. Do negative 4 times negative 1 is positive 4. Add negative 4 plus 4, and I get 0. Now, by the way, I should get 0 because that's my remainder. And if something is a solution, then that means that when you plug in that value of x, you get 0. So I should have a remainder of 0 if I've done synthetic division with a solution. So what I've actually just figured out here is that the expression 2x cubed minus 5x squared minus 11x minus 4 is the same thing as x plus 1 times, now these are basically the coefficients. So it's like I put an x squared there, an x, and then of course x to the 0, which is the same thing as 1. So I have taken 2x cubed minus 5x squared minus 11x minus 4, and I have factored it into x plus 1 times 2x squared minus 7x minus 4. Now this question is asking us to describe the other two solutions. Are they real or are they complex and therefore imaginary? So I need to now basically figure out from 2x squared minus 7x minus 4, do I have two real solutions? Do I have one real solution? Do I have two non-real solutions? So there are a couple ways that you can do that. First, I hope you guys remember the trick with b squared minus 4ac. So we can use that trick to basically see is b squared minus 4ac positive, 0, or negative. That could at least tell us if the solutions are real or non-real. But then if they are real, we're going to have to take, oh sorry, I forgot to put equals 0 and equals 0 for both of those. We're going to have to take this 2x squared minus 7x minus 4 and factor it. So let's first do b squared minus 4ac. And let's see, is that a positive value? Is that 0 or is that negative? So b, this one's b, here's a, and here's c. Because remember, when you set up that quadratic, it's in the form ax squared plus bx plus c. So b is negative 7, so I have negative 7 squared, minus 4 times a, which is 2, and c, which is negative 4. Well, that's going to end up being a positive number because I'm going to have 49 plus 32, right? I don't really care. I don't have to do that addition. I just have to know that that's a positive number. And if it's a positive number, that means I have two real solutions. So first thing I can do is cross out any answer choices that say that it's a complex one that's not real. Here's a complex one that's not real. So A and E are out. We know that we have two real solutions, but we don't know if they're positive or negative. So for us to know that, we're going to have to factor. So I'm going to have a 2x and an x, and I have to think to myself, okay, what multiplies to negative 4? Well, I could use plus 4 and minus 1, I could use minus 4 and plus 1, or of course I could use plus or minus 2. Well, the answer is going to be to have a minus 4 here and a plus 1 here. And let's review why that's the case. If I were then to kind of take this where I've just factored and FOIL it, remember I'd have 2x times x is 2x squared. I'd have 2x times negative 4, which is negative 8x, but then I would be adding the 1x for those inner terms, which is exactly what we want, negative 7x. And then when I multiply those last terms, plus 1 times minus 4, I get minus 4. So after all this work, we basically figured out that x is negative 1. We already knew that though, but from the other terms where we use synthetic division to simplify, we get that x is negative 1/2, and we get that x is 4. So of the additional answers, one of them was negative and one of them was positive. So it looks like the correct answer is C. Oh my gosh, so much work. We have the same thing for this next question. For this next question, you could do long division. And when you do that long division, you can set it up, right, that you have 5x cubed plus 4x squared plus 5x plus 6, and you're going to divide. Again, if negative 1 is the solution, then x plus 1 is your factor. But for this question, again, I want us to use synthetic division just to get a little bit more practice. So synthetic division, here we go. So I'm going to put my negative 1 up here. Then I'm going to put my coefficients, 5, 4, 5, 6. Remember that it's a little bit different steps. We're going to be adding, and I start by carrying down the 5. 5 times negative 1 is negative 5. 4 plus negative 5 is negative 1. Negative 1 times negative 1 is positive 1. 5 plus 1 is 6. 6 times negative 1 is negative 6. When I add those together, I get 0 as the remainder, which is exactly what I want because remember, it's a solution. So if it's a solution, we have to have a remainder of 0. So I have now figured out, right, that I've basically taken my original polynomial, 5x cubed plus 4x squared plus 5x plus 6 equals 0. And that is the exact same thing as x plus 1 times, I can use these terms for a, b, and c, 5x squared minus x plus 6. So for us to know what is true of the other two solutions, are they real or not real, let's use our same trick with b squared minus 4ac. Is that positive, in which case we'll have two real solutions? Is it 0, in which case we have one real solution? Or is it a negative number, in which case we have two imaginary solutions? So here we go, b squared minus 4ac. So our b is negative 1. So I'm going to have negative 1 squared minus 4 times a is 5. And c is negative 6. Oh, sorry, positive 6, not negative 6. Let me rewrite that. It's positive 6. So then what happens? We have 1 minus a big number, right? We basically have 1 minus 120. That is a negative number. With a negative number, we have two imaginary answers. Remember, if b squared minus 4ac is negative, the answers are imaginary. So that means that they are both, right? The other two solutions are complex numbers that are not real. So the correct answer is A. Okay, we have one more. And actually, wait, let me go back. Before we do this last one, I want to make sure that I really make something clear. Let me get a new color here for my pen. When I put a number over here, it's basically the same thing as plugging in. So I'm basically saying if I put x equals -1 and I plug it in here and plug it in here and plug it in here, this is the answer that I'm going to get. So the remainder, when you do synthetic division, basically reflects what answer do you get when you plug in that value for x. If something is a factor, right, or a solution, then of course the remainder is 0. If something is not a factor and is not a solution, so it's not one of the x-intercepts, then whatever value you get here is basically the same thing as whatever number you get here when, again, you plug in that value of x. So knowing that information, let's solve this next question. It is telling us that we have some sort of polynomial, p of x, that when we do p of 3, so when you take the value of 3 and you plug it into each part for x, it equals -2. So if you think about that the same way we just talked about with that synthetic division setup, we have the coefficients for our polynomials here, we have a 3 here, and then we have a -2 here. Now remember, what did that mean? That meant that if I plug x equals 3 in, my answer is -2. Well, that means that x minus 3 is not going to be a factor, because remember, for something to be a factor, the remainder equals 0. So the first thing I'm going to do is cross out answer choices A, B, and C, because we definitely don't have a factor here because we have a remainder. The remainder is -2. For something to be a factor, remember, for a factor, we've got to have a remainder of 0, which we don't have here. We've got a remainder of -2. So what that means is that when you take p of x and you divide it by x minus 3, because remember, putting a positive 3 here is the same thing as doing long division with x minus 3, that if you do all this work, your remainder is going to be -2. Well, with a remainder of -2, remember that basically means the same thing as when you plug in 3, you get -2. So the correct answer to this question is that we have a remainder, and the remainder is -2. Because remember, for answer choice option D, if the remainder is 0, that means it's a factor. So technically, answer choices A and D mean exactly the same thing. And then the problem, of course, with B and C, we had several problems. First, nothing is a factor here because we don't have a remainder of 0. Second, we're not even talking about numbers either 2 or -2. So those were just kind of there to trick you. So this last question, again, the goal was to kind of pull together everything that you learned about long division and synthetic division and apply it to this really hard question that just makes sure that you actually understand what it means when you're doing long division or when you're doing synthetic division. What does that remainder mean? And remember, the remainder is the value that you get when you take that value of x and plug it into the polynomial. What answer do you get? That is your remainder. Okay, so before we jump into matrices, I want to make sure that you understand a very basic rule with matrices. And the rule is that when you write out the dimensions of a matrix, you always write out the dimensions as rows by columns. So I like to think of it as R by C. So if we look at option W, right, we have 2 rows and 2 columns. So W matrix is a 2 by 2. Same thing for matrix X. We've got 2 rows, 2 columns. It's a 2 by 2. Matrix Y, we have 2 rows and now we have 3 columns. So this one's going to be a 2 by 3. For matrix Z, we have 3 rows, 2 columns. It's a 3 by 2. Now, why do we care about this? Well, you've got to know this basic rule with how to set up these dimensions. Then you have to understand that when you want to have a product for matrices, which of course means that you are multiplying matrices, there's actually a really simple rule for you to know if you can multiply matrices or not. So that's the goal of this question, is for me to teach that to you. So matrix W is a 2 by 2, and they're asking us if we can multiply matrix W, which is a 2 by 2, times matrix X, which is also a 2 by 2. Well, the way that you can know if you can multiply matrices is if these inside numbers match. Because they're both 2's, that means that we can multiply them. But remember, we're looking for the one that we cannot multiply. So because we can do W times X, or matrix W times matrix X, I'm going to eliminate A. Let's check B. Matrix W is a 2 by 2. Matrix Y is a 2 by 3. Well, guess what? Those inside numbers match again, right? We have 2 and 2, which means that I can multiply the matrices together. What about C? Matrix Y is a 2 by 3. Matrix Z is a 3 by 2. Guess what? Those numbers match on the inside, so I can multiply those matrices. So I'm going to eliminate it. What about X times W? So X was a 2 by 2. W is also a 2 by 2. Guess what? Those inside numbers match. They're both 2's, which means that I can multiply, so D is out. Looks like E is going to be our answer. So matrix X is a 2 by 2. Matrix Z, aha, is a 3 by 2. There we finally have our mismatch. The 2 and the 3 don't match, so you can't multiply those matrices. So the correct answer to this question, remember, we're looking for the one where you cannot do the multiplication, you cannot find a product, is option E. We cannot multiply a 2 by 2 matrix times a 3 by 2 matrix. One thing too that I want you to also understand, I'm just going to kind of bring one example over here, is if I try to do a 2 by 2 times a 2 by 3, first, I look at these inner numbers to make sure they match. That's how I know, yes, I can multiply. But then the next thing that's good for you to know is that when I multiply these matrices, my answer matrix will be a 2 by 3 dimension. So you use those inner numbers to make sure they match, which means yes, you can multiply. Then the outer numbers actually tell you, hey, when you multiply these matrices, here will be the dimensions of that product. Now this next question is very similar to the one that we did before. It's basically asking us, can we multiply these matrices together? Because we're looking for the one that's not possible. So matrix E times matrix D is going to be an N by M, M by K. Guess what? M's match. That means it is possible, so it's not our answer because we're looking for the one that's not possible. D times C, matrix D is an M by K. Matrix C is K by N. Those inner letters match. So B can be multiplied, so it isn't not possible. Sorry about the double negative. It is possible, right? So we're going to cross out that answer. C, matrix C is a K by N. Matrix E is N by M. Aha, we're matching on that inside. That means we can multiply. What about option D? AC, matrix A is an M by N. Matrix C is K by N. Well, guess what? We cannot multiply because that N and K don't match. So if we're looking for the one that's not possible, D is not possible. We cannot multiply matrix A times matrix C, which, by the way, is different from doing matrix C times matrix A. So you have to always make sure that you preserve the same order. Let's just double check for extra practice that we're good with with option E. A is an M by N, E is an N by M. So guess what? Those N's match. Yes, it would have been okay to do A times E. So D is the correct answer because, again, it's the one that is not possible. And when those inner ones don't match, that means you can't multiply the matrix. Okay, the next thing we're going to talk about is what do you do when you've got this little number on the outside of a matrix? Like, do you multiply it and kind of distribute that through? Does it get divided through? Does it get added through? People get very confused, but it's actually super simple. You're basically going to take the 3 and multiply to each quadrant of your matrix. So what I'm going to do is basically redraw this 2 by 2. I'm going to kind of put little tick marks just to show clearly which quadrant. So in this upper left quadrant, basically I'm just going to take that 3 and then multiply it by the -1 that's in there. Lower left, have that 3 on the outside times the 0. Upper right, I've got my 3 on the outside times the number, which is a 3. And then I still have my 3 on the outside times the -4. So again, what I did here, right, is I took this 3, I'm going to kind of have that purple 3, and basically just distributed it, and I am multiplying to each part. So then the final answer here, when I've multiplied these matrices, or excuse me, when I've multiplied the coefficient by the 1 matrix, I have -3 in the upper left, 9 in the upper right, 0 in the lower left, and -12 in the lower right. So it looks like my correct answer is E. Last one with matrices. So in general, I always recommend that when students have to multiply matrices that you use your graphing calculators to do those functions because it's way easier and way faster. In our lesson, Intro to the TI-83 and TI-84 calculator, I show you how to use the calculator to multiply matrices. For this question, I'm just going to kind of write it out by hand, but again, it's going to be way faster to use your calculator. But because for this one, we're really just kind of multiplying one set of rows by one set of columns, it's easier to write it out. But if you ever ended up with more than one of each, like you have 2 rows or 2 columns or 3 of each or 4 of each, you do not want to do it by hand. You definitely want to use your graphing calculator. So first things first, let's make sure we can do this multiplication. So I have 3 rows by 1 column, so I have a 3 by 1 matrix. Then I have 1 row by 3 columns. So first thing I can do is verify, yes, I can multiply these matrices because those inner numbers match. Then I can know, well, guess what? My answer, when I do this multiplication, is going to be a 3 by 3 matrix. So the first thing you can do here is look at your answer choices and get rid of C, D, and E because those are not 3 by 3 matrices. Only A and B are. So even if you didn't know what to do from this point, you have 1 second left and you have to bubble something, at least you've got a 50-50 shot, right, for a guess versus having to choose among 5 answer choices. Okay, so now what I'm going to do is I'm going to draw out for us kind of a big version of this 3 by 3. I'm going to kind of put these tick marks again just to make it really easy for you to see what is in each quadrant. Now, what you're going to do when you multiply matrices is you basically do a column, or excuse me, you go 1 row at a time times a column at a time. So basically what I'm going to do is I'm going to take my first row, which is x, times my first column, which is 1. So I'm going to have an x times 1. Then I take my second row, 2x, times my first column, 1. And then I take my third row by my first column, which is 3x times 1. And then I'm going to just do that over and over and over again, but basically moving to the right and changing the column each time. So I take my first row, actually let me change my color to make it a little easier for you to follow. I'm going to take my first row, x, but now multiply by the second column, 0. Second row, 2x, times second column, 0. Third row, 3x, times second column, 0. Then for the last one, we're going to do the same thing again, but now we're going to use our third column. So first row, x, times that third column, -1. Second row, 2x, times that third column, -1. Third row, 3x, times that third column, -1. So it looks like the correct answer to this question is going to be option B as in boy. We have x, 2x, 3x, then we have all zeros, and then we have -x, -2x, -3x. So the correct answer is option B as in boy. Again, multiplying matrices is super complicated. I definitely recommend you use your graphing calculator because it will save you time. The only reason I did this one by hand is because, you know, we just had 1 column and 1 row. to be able to kind of expand out this matrix multiplication. In general, most important takeaways for matrices: number one, you've got to know that their dimensions are written as row by column. You have to know the rules about how do I know if I'm allowed to multiply? Well, you know you're allowed to multiply if the inner numbers match. And then the last main takeaway is that what are the dimensions of the product matrix after I've multiplied them? And it's kind of those outside numbers. So for our segment on vectors, we're going to go over 2 questions with vectors. So they're kind of the least frequently tested of the rare and random topics, but just good to expose you again to these 2 main examples showing you kind of 2 main concepts that come up with vectors. So the first thing I want to make sure that you understand about vectors is that anytime they ask you to add vectors together, anytime you add a vector, or even if you're subtracting vectors, if you're combining them, you always do it tip to tail. So what does that mean? That means that if I want to take vector AB, so if I look at vector AB, it moves to the right, I think it's 9. Let's see, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I go up 1, 2, 3, 4, 5, 6. Okay, so that means that vector AB goes to the right 9 and up 6. So I'm just going to kind of use that notation to indicate for myself I go right 9, up 6. So if I were to replot vector AB starting at the origin 0, 0, I would go to the right 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 6. Okay, so I would then have my point here, connect them, and that is vector AB. Now, if I want to take vector AB and I now want to add vector CD, well, looking at vector CD, it doesn't move to the right or the left at all, but it just goes up by 1, 2, 3, 4, 5. So vector CD has 0 movement to the right or left, and then it goes up 5. So that tip to tail, as I was talking about, basically means that if I want to add vector CD, I'm going to take the tip of AB and put the tail of CD in the same place. And then CD from that point is going to go up 5. 1, 2, 3, 4, 5. So let's say that's about there. So there's vector CD. So now the question of, well, if I'm adding AB plus CD, what does that look like? It basically means I go to the same starting point and the same ending point, and when I connect those, that becomes AB plus CD. So that vector AB plus CD goes to the right 9, and then it went up 6 to get here, but then it went up 5 more, so it went up 11. So that means that vector AB plus CD goes to the right 9 and up 11. So what you now have to know is that kind of in the way that we describe, the coordinate plane with vectors, is that a vector with kind of this form of 9, 11 is written as 9i plus 11j. So when I put these vectors together, when I add them tip to tail, my answer is that I'm going to the right 9 and up 11, which is the same thing as 9i plus 11j. So the correct answer is E. Next question. This one is asking us to find 2 times vector u plus -3 times vector v plus vector w equals 0. And they're asking us to find what is the component form. So the component form is what I showed you before, like where it kind of has those brackets and then the 2 numbers inside. It's basically saying how far do we go to the right and the left. So the question is asking us to solve that for vector w. So here we go. I'm going to have 2 times vector v, or excuse me, vector u. Vector u is 4, 3. I'm going to have that plus -3 times vector v, which is going to be 2, -7. I have that plus vector w equals 0. Now all you have to do with this number is just distribute it to both. So 2 times 4 becomes 8, 2 times 3 becomes 6. Plus, negative 3 times 2 is negative 6, negative 3 times negative 7 is 21. Plus vector w equals 0. Well, now I can just add those other pieces together. So I can do 8 plus negative 6, and then I can do 6 plus 21. So when I add them together, I get 8 plus negative 6 is 2, 6 plus 21 is 27, plus vector w equals 0. Well, now I can figure out what vector w is, right? Because if I'm adding across and I get 0, well, if I start with 227, then I'd have to add negative 2 and negative 27 to be able to get 0. So that means that vector w is negative 2, negative 27, so the correct answer is B. Okay, so that concludes our review of these rare and random math topics that come up on the ACT and SAT. Again, we touched some concepts that do not come up very much, but when they do, it is critical that you know how to solve them, especially if you're going for that super high score. So I hope that this review was good. I know this was a long lesson, so hopefully you're able to break it up into different topics to make it more digestible for yourself. But again, thank you for studying with me and good luck with your exams.